Excellent. Well, thank you everyone for joining our seminar today. For your information, the seminar is being recorded and will be made available on the RemPlex web page. And as a reminder, we request that you please keep yourself muted during the presentation and Q&A. My name is Alicia Gorton with Pacific Northwest National Laboratory, or PNNL, and I'll be moderating today's seminar on behalf of the Center for the Remediation of Complex Sites, or RemPlex. RemPlex is a PNNL platform that couples unique core competencies and expertise with state-of-the-art facilities and physical assets to deploy, mature, and develop advanced technologies to solve complex issues of contaminated subsurface environments. And so today's seminar by Nick Qafoku and Amanda Lawter of PNNL will discuss calcium carbonate minerals as scavengers of metals and radionuclides for natural attenuation and remediation. Nick Qafoku serves as the Deputy Director of Outreach and Engagement of RemPlex, and he is a Chief Scientist and leads the PNNL Interfacial Geochemistry team. He is internationally recognized for 30 years of expertise and leadership in the soil chemistry and geochemistry communities. Amanda Lawter joined PNNL in 2011, and she has worked primarily on contaminant research as well as groundwater impacts of carbon sequestration. Her work has included fate and transport of contaminants at the Hanford site and testing potential remediation technologies for multiple contaminants using batch and column studies. During and after the presentation today, I encourage you to submit any questions you have via the chat box, which will be monitored, and those questions will be passed along to Nick and Amanda. I'll be posting a link in the chat box to a RemPlex survey where we invite you to provide feedback on today's seminar and also offer recommendations for future topics. So with that, I will turn it over to Nick to kick us off. Nick.
Thank you so much, Alicia. Good afternoon, everyone. The presentation today will be focused on the role of the calcium carbonate minerals as host for contaminants. And this is definitely an important topic for the complex sites, and as it is an important topic for the RemPlex as well. And this is because calcium carbonate minerals affect significantly contaminants mobility, are contributors to the natural attenuation of contaminants, and they may be included as part of remediation strategies as well. I would like to emphasize that the calcium carbonates are important and key contributors to the overall fate of contaminant in the complex sites. This contribution needs to be carefully addressed and fully understood, mainly because it is prevalent and widespread and significantly impact the mobility of many contaminants of concerns and environmental risk drivers. Other important reasons are calcium carbonate are important sinks and sources of carbon. In his latest book, Robert Hazen, the book was published in 2019, entitled Symphony in Sea, Carbon and Evolution of Almost Everything. He wrote, the story of carbon is, in a sense, the story of everything. So I'm sure that you will be hearing a lot about the inorganic carbon cycling, calcium carbonate, in the next 5 to 10 years. I wanted to emphasize at the beginning that the Earth Sciences Division here at PNNL has a strong program on calcium carbonate geochemistry and interaction with contaminants. Some of the results will be presented in today's talk. In addition, we are putting together a review paper that we will publish soon in early 2021. In addition to the EM-funded research here at PNNL, there is a lot of calcite or calcium carbonate related research funded by the BES and BER offices of the Department of Energy, the programs of the Office of Science in the Department of Energy. These programs mainly focus on the molecular nanoscale properties of these minerals. They look at the aggregation and crystal growth, which are very, very helpful in understanding different aspects of contaminant interaction with this mineral. So overall, the program of the calcium carbonate geochemistry here at PNNL and at RemPlex as well is a pretty strong program. The presentation today has three major parts. The introduction part. The second part is going to be about interactions of calcium carbonate minerals with contaminants, mainly focusing on chromium, uranium, and iodine. And the third section will address contribution to natural.
That was weird.
Strategies. Next slide, please. Calcium carbonate minerals, they are abundant and they are very important in the environment. Limestone, mainly calcite, and sedimentary metamorphic rocks, mainly dolomite, are exposed at about 20% of Earth's surface. Calcium carbonate minerals make up 4% of the Earth crust. In decreasing order of importance, calcite, dolomite, magnesium calcite, aragonite, and magnesites are listed in the book by Langmuir, 1997. Calcium carbonate coating also occur in the sediments, and they have an important effect on the mobility of contaminant, even when the coating are thin, because they cover the surfaces of other reactive phases, such as iron and manganese oxides and phyllosilicates, rendering them less reactive. I still remember a quote from the Donald Langmuir book that I'm citing right now. As a rule of thumb, when carbonate minerals are present in a silicate or aluminosilicate rocks or soils at a level of about 1% or more, they will tend to dominate the chemistry of the soil or groundwater. So this actually states the importance of these minerals in soils and sediments. Next slide, please. This slide shows the reaction of formation of calcium carbonate. I wanted to emphasize here the participating aqueous species, as well as the controlling chemical reactions that are part of the major reaction of formation of calcium carbonate minerals that involve species in the gas, aqueous, and the solid phases. I will like to read here the quote recently published in Science. The interface between minerals and aqueous solutions hosts globally important biogeochemical processes, such as the growth and dissolution of carbonate minerals. These minerals participate in multiple processes and reactions, controlling and affecting the cycling and fate of nutrients and contaminants, and the quality of surface water, pore water, and vadose zone aqueous phase, and groundwater as well. Next slide, please. Another important aspect and how the calcium carbonate are important in environmental system is that they are strong buffers against pH changes. In complex site, for example, there are sediments that have been exposed to acidic waste, and as a result, they are exposed to solutions that have lower pH. The decrease in pH actually causes enhanced weathering of the minerals and a bunch of other related, simultaneous, or sequential reactions. Now, the calcium carbonate actually serve as strong buffers to the changes in pH, and this is very important because there are cases when during the dissolution of the minerals, there are contaminants that are mobilized and the pore water or the groundwater becomes more contaminated. Next slide, please. I would like to give you an example of some studies that Amanda Lawter actually did a couple of years back, where she studied the effect of two sediments from the Kansas High Plain Aquifer that had different calcite concentrations. One of them actually had no detectable calcite, depicted here in this graph with a red plot. And then the other one had a substantial amount of calcite in them. And you can see here that the one that had calcite was able to buffer the pH much higher than than the one that did not have calcite. This is very important because in the plot here to the right, the amount of arsenic that was released from these sediments was significantly different. The amount of arsenic that was released from the sediments that did not have a buffer capacity, did not have calcite, was much higher in this case. Next slide, please. One other aspect of the calcium carbonate minerals is that they are able to affect the iron phase transformation that usually occur in soils. And in this study that was just published in the Environmental Science and Technology, they also show that elevated carbonate bicarbonate activity in the aqueous phase was able to control the transformation of ferrihydrite to either hematite or goethite. And bicarbonate ions present in the aqueous phase promoted transformation of ferrihydrite to hematite while retarding the goethite formation. So the activity of the carbonate and bicarbonate in solution had strong control over iron phase transformation and iron cycling in oxic environment. This is very important for the complex sites because in some of them, ferrihydrite is considered as a great sorbent and can be used as part of some remediation technologies to remove contaminants. But it is very important to understand the phase transformation at ferrihydrite in those sites as well. And this study that links together the calcium carbonate dissolution and the carbonate activity, bicarbonate activity ions in the aqueous phase is very important. Next slide, please. There are three polymorphs in the calcium carbonate: calcite, wetherite, and aragonite. Calcite is the most common and is stable at atmospheric pressure. Aragonite is found in high pressure environment and hot springs as well. And wetherite is a rare mineral that only forms from solutions that are highly supersaturated with respect to either calcite or aragonite. But one point is of great interest, that wetherite usually transforms quickly to calcite. And we will see later in this presentation that this is very, very important when we are talking about chromium incorporation into initially wetherite and later in calcite. The importance of metastable wetherite form of calcium carbonate is increasingly appreciated as an intermediate between amorphous calcium carbonate that usually occurs in many soils and sediment and more stable forms like the crystalline polymorph type of calcite and aragonite. Next slide, please. As I mentioned at the beginning, calcium carbonate are host of radionuclide, metals, and metalloids. They are host of uranium, iodine, chromate, strontium, arsenic, copper, selenium, and many other potential contaminants. Some of them are listed in this slide. The focus of our presentation today will be chromium, uranium, and iodine. And I will actually yield the floor now to Amanda. She is going to talk about the incorporation and interaction of calcium carbonate with chromium.
Thanks, Nick. As Nick said, the first contaminant that we'll be talking about today is chromium. Hexavalent chromium, which is a toxic form of chromium, is used in many different industrial processes, which has resulted in a variety of chromium contaminated sites worldwide. Laboratory studies have shown that chromium can be incorporated into calcium carbonates. And they've also shown that an increase in the initial concentration of chromium will also increase the amount of chromium that's included in the precipitating solid. The figure shown here is an example of one such study where we have the concentration of co-precipitated chromate on the y-axis and increasing initial chromium concentrations shown from left to right on the x-axis. As the chromium concentration increased, the amount that was incorporated into precipitating calcium carbonates was also increased. For chromium, the chromate ion is able to substitute directly for the carbonate ion in the calcium carbonate. When chromate is present, it can have a major effect on the crystal growth of calcium carbonates. Having chromate present can increase the nucleation density of those carbonates and also can reduce the size of the resulting crystals up to 50%, and also increases the ratio of vaterite to calcite. The SEMs shown here are an example of some crystals that were grown in the presence of chromate. You can see that there's a large variety of crystal shapes in comparison when only in the absence of chromate with just calcium carbonate precipitating, just the bottom two right general shapes were seen. So it was a lot more consistent and less variability in the absence of chromate. The XRD spectra shown here are from another experiment where calcium carbonates were precipitated in the presence of chromate. In this case, the bottom spectra is showing a calcium carbonate with no chromate present. And as you move up the lines, the calcium or the chromium concentration was increased. You can see that as that chromium concentration is increased, the calcite peaks that are indicated with red arrows are decreasing, while the vaterite peaks indicated by the blue arrows are increasing. The presence of chromate in the system can not only promote the formation of vaterite, but it can also delay or prevent that vaterite from transforming into the more stable calcite. This is one more example of a study. This one was conducted here at PNNL, where we precipitated calcium carbonates in the presence of chromate, which is shown in the SEM micrograph on the right. And we were forming vaterite. While without the chromate present, we were forming calcite, shown on the left. The reason that this is important is because, as Nick said in his introduction, the vaterite polymorph is much less stable than calcite, which has some implications in remobilization of that incorporated chromium. So now we'll look at the chromium at the Hanford site. At the Hanford site, hexavalent chromium was used in the coolant water as an anti-corrosive. You can see in the plumes indicated here in blue and yellow that most of the hexavalent chromium occurs right along the river corridor. That's because that's where the nuclear reactors that use the coolant water, as well as the water treatment plants where that hexavalent chromium was added to the water, were located. To determine the mineral associations of the chromium at Hanford, we've used several different sediment characterization techniques. In the photograph on the left, you can see an example of some sediment and rocks that were collected from the Hanford site, and the yellow staining in the top left of that rock is indicative of chromate. On the right, we have two plots showing one of our sediment characterization techniques, which is sequential extractions. Essentially, with these extractions, we use increasingly aggressive extractants, which mobilize different phases, will extract from different phases so that we can determine where the chromium is most associated with. The top plot is showing a hexavalent chromium, and the yellow and orange colors indicate a carbonate phase. In comparison, the chromium-3, which is less toxic and less mobile, is more associated in the bottom plot with the dark green coloring, which is associated with the less mobile, hard to extract phases. So we can see using this technique that the chromium found in this specific sediment at the Hanford site was indeed mostly associated with carbonates. With that, we'll go back to Nick, and he will talk about our next contaminant, which is uranium.
Uranium is a very important contaminant. It is present in many natural environments and contaminated sites around the globe. Both uranium-6 and uranium-4 can be incorporated into calcite However, hexavalent uranium-6 is usually more mobile than tetravalent uranium-4, and it's more relevant for consideration of calcium carbonate attenuation mechanisms. Uranium-4 typically forms other low solubility precipitates under chemically reduced conditions, although it can be reoxidized readily to uranium-6. Two main mechanisms are involved in the interactions between uranium and calcium carbonate polymorphs, adsorption and co-precipitations, and these are the ones that I will be covered shortly in this presentation. There are other relevant calcium carbonate mediated reactions, such as the one that facilitates sequestration of aqueous uranium by providing either calcium or carbonate ions via calcium carbonate dissolution. Or the other aspect has to do with the fact that sometimes the carbonate coating might actually hinder the uranium interaction with reactive minerals, such as, for example, phyllosilicates or iron oxides. To the right, I am showing a diagram that was published by Zaccoli et al. In 2013, indicating the complex aqueous and solid phase speciation of uranium. This is a topic that I will come back later in the presentation. Next slide, please. As far as the adsorption of uranium to calcium carbonate, the factors that control the extent and rate of uranium sorption are uranium-6 loading. Multiple uranium species can be formed when the different concentrations of uranium-6 are present. Another factor is the calcium concentration, and another big factor is the pH. And the importance of these factors is actually depicted in the two plots that are presented to the right of this slide. The one at the bottom shows the adsorption, the percent of uranium absorbed as a function of pH in two systems, the one that had calcium actually in the aqueous phase, and the one that did not have calcium. The one that had calcium actually absorbed much less uranium in the interval from pH 7.2 to pH 8.4. While in the absence of calcium, uranium got absorbed much more. And if you see the speciation in the top diagram, in the presence of calcium, you have the predominance of a calcium uranate carbonate species that is uncharged. And in some cases, that is hard to absorb in surfaces like the calcium carbonate minerals. And that's the reason why we see less absorption from pH 7.2 to pH 8.4 in the system where calcium was present. This actually these examples actually stress the importance of the aqueous speciation of the uranium. And to give you a flavor of what I mean by that, I included this slide here. It's pretty crowded. And I don't expect you to go over all the details of it, and I will not. But I'm just showing how complex the aqueous speciation of uranium can be in the presence of different variables like the PCO2, calcium and magnesium concentrations, as well as phosphate concentrations that might be present as well. Next slide, please. I'm showing here some results that we collected from experiments that were conducted with sediments coming from the TX tank farm at the Hanford site. And this was kind of a unique sediment because this was coming from the Cold Creek Paleosalt that is collected at a depth of 110 feet below the ground. The calcite concentration of that layer is about 33 to 35%, so it's very high. What we did, we conducted two experiments with sediments packed in columns where we applied different residence time, fluid residence time, and we were looking at the uranium release in the effluent. And we saw that the release of the uranium was independent of the fluid residence time. And we looked carefully to determine what was the mode of absorption or interaction of calcium carbonate minerals, calcite in this case, with uranium. And we discovered that most of the uranium that was present was in the surfaces and was stored on the surfaces of these minerals. One point I wanted to make clear here is that in addition to the fact that this layer can serve as a barrier, as a natural barrier of the movement of uranium through the profile, through the battle zone profile at the Hanford site, because it does have sorption capacity and can sorb a significant amount of uranium. But in addition, if under some different conditions, this actually layer can serve as a source of uranium as well. And this is the thing that we discovered during these experiments that were conducted almost a decade ago. Next slide, please. There has been a lot of discussion in the literature, especially at the beginning of this century, whether or not the uranium-6 can be accommodated inside the calcite structure. And there have been a lot of publications debating under what conditions and what are the optimum conditions and what is the environmental molecular environment surrounding the carbonate that are included in the calcium carbonate structure. I don't want to go to the details here, but there were a couple of publications by Shelley Kelly in 2003 and one other in 2006 that actually nail it down, and they presented evidence that uranyl-6 can be accommodated inside the structure of the calcium carbonate. And later on, next slide, please. We did some experiments with the 300 area sediments at the Hanford site, and Jiming Wang actually was able to figure out that there was uranium substituted into calcite present in those sediments. And as far as I know, this was the first time that such a thing was shown actually in the calcium carbonate that occurs naturally into subsurface settings. The only thing that actually Jiming noticed during this study was that the substitution site within the crystal structure of calcite showed local aragonite-like structure, which was kind of an important, because this brought another set of studies that look carefully at the differences between aragonite and calcite in terms of accommodating uranium structure. Next slide, please. In terms of incorporation of uranium into the calcium carbonate, we also did some experiments with the sediments coming from the TX tank farm. This is a much shallow sediments at 69 feet below the ground. It does have a lower concentration of calcite, but all the spectroscopic analysis that we did confirmed that uranium-6 actually was indeed incorporated into calcite. And the graphs that are included in this slide to the right actually shows how dynamic is the release of uranium from this sediment when it was leached with a uranium-free solution. This is kind of an important finding as well, because directly shows and provide evidence that the calcium carbonate minerals are important and significant in controlling the transport and fate of uranium in the Hanford sediment. And with that, I will yield the floor back to Amanda to continue presenting some data on the iodine interaction with calcium carbonate minerals.
Thanks, Nick. So now we'll start talking about the interactions between iodine and calcium carbonates. Iodine is a common contaminant at nuclear waste sites, and the interaction of the iodine waste with calcium carbonates has been well studied. However, the iodine in regards to nuclear waste is geologically speaking relatively new. So we can also look at natural analogs to learn more about some long-term interactions between iodine and calcium carbonates. For example, iodine has been found in both speleothems and carbonate shells. And the micro XRF or micro X-ray fluorescence spectra shown on the right here is one example of what we can learn. The spectra shown in blue is a well-preserved carbonate shell, and you can see a clear iodine peak for that blue well-preserved shell. The red spectra represents a carbonate shell that's undergone recrystallization. And in that case, the iodine peak is no longer there, indicating that the iodine could be lost through recrystallization of calcite. The speciation of iodine is really important when it comes to interactions with calcium carbonates. Many laboratory studies have shown that while iodate, the oxidized form of iodine, can be incorporated into calcium carbonates, the reduced form iodide cannot. The plot shown here is showing just that. On the y-axis, we have an iodine to calcite ratio, and on the x-axis, we have an increasing concentration in initial iodine. The black circles show a good correlation, like we saw with the chromate, where an increase in initial concentration of the iodate resulted in an increased amount of iodine incorporated into the calcite structure. That's shown in the black circles in that plot. In comparison, the iodide is shown in the open circles that are essentially at zero incorporation into the calcite structure, irregardless of the initial concentration of iodide. This incorporation of iodate and not iodide is so consistent that it has been suggested that iodine could be used in the rock record as an indicator of oceanic anoxic events. When the ocean becomes anoxic, it would be expected that the iodate would be reduced to iodide, and that iodine would therefore be reduced in concentration in the rock record. Here at PNNL, we conducted some ab initio molecular dynamics modeling to determine how the iodate was getting incorporated into calcium carbonate structure. The iodate anion has a -1 charge, and the modeling found that the iodate was being substituted with carbonate, but carbonate is a -2 charge, which means that there had to be some charge compensation. The modeling also showed that that charge compensation is coming from most likely a sodium or hydrogen, which are both +1 charge. We use the same modeling technique to determine if the iodate incorporation mode was the same when there were co-contaminants present. In this study, we used chromate. In the laboratory study, the presence of chromate reduced the amount of iodate that could be incorporated into the calcite structure by about 24%. But the modeling revealed that the mode of substitution remained the same. This modeling also revealed that in both cases, with or without the co-contaminant present, the iodate was mostly incorporated just into the surface of the calcite. We wanted to look more into that, and so we use nanosims or nanoscale secondary ion mass spectroscopy or spectrometry, as well as TEM and EDS to show that indeed the iodine seems to be incorporated only along the surface of those calcite particles. Now, this has important implications when it comes to remediation and mobilization of the iodine, as it would be expected that the iodine is more easily remobilized if it's located along those surfaces. In addition to incorporation into calcium carbonates, the iodine can also be adsorbed onto the surface. These two plots show results of some of the calcite testing we've done here, where the blue lines towards the top are showing just adsorption of iodine onto calcite, while the lower purple lines are showing adsorption combined with incorporation into the calcite structure. In both cases, the initial iodate concentration was 50 parts per billion, which is shown on the y-axis. And you can see that the blue lines show some removal of iodate, but much more iodate is removed when it's also allowed to incorporate into the calcite structure. We wanted to look more into these calcites that we've produced here at PNNL. So in the XRD spectra, you can see on the left, these represent a variety of calcites that we've produced with initial iodine concentrations ranging from 50 to 500 parts per billion. And each one of them is showing that we produce pure calcite. We also wanted to see if the stability of these calcites was affected by the incorporation of iodine, especially with that iodine right near the surface of the particles. The mobility would be largely affected if that also affects the stability of the resulting calcites. So on the right, we have the results of our solubility testing, where we have the solubility determined by the calcium concentration shown on the y-axis with the pH shown on the x-axis. The red triangles are showing a pure calcite that was commercially available in comparison with the blue circles and the green squares that represent our calcite that either had 250 parts per billion or 500 parts per billion initial iodine concentrations. In both cases, the stability of our calcite lines up really well with the commercially available pure calcite. So we found that the stability of the calcite is not affected when iodine is incorporated into the structure. Looking at iodine specifically at Hanford, here is a map of the iodine plume, which is mostly located in the central part of the Hanford site, known as the Central Plateau. The iodine is a product of plutonium production at the Hanford site. And the reason that iodine is a really tricky contaminant to remediate is because it has a long half-life, so it will not be decaying anytime soon. And it also has a relatively low drinking water standard of 1 picocurie per liter. In comparison, uranium is 10 times that at 10 picocuries per liter. In addition, specifically at Hanford, the iodine plume is very large and very dilute, which also creates a challenge when we're trying to remediate it. As with our chromium, we used sequential extractions to determine which phase the iodine was associated with. And again, the iodine was associated mostly with carbonates in these example sediments. And those are represented by the yellow and the orange in this plot. You can also see that a fair amount of the iodine in the sediment was associated with the light green, which is a representative of iron oxides. In a study by Zhang et al., they also found that their groundwater samples were significantly affected by the calcite precipitation and incorporation of iodine. While pulling up their groundwater samples to the surface due to CO2 degassing, calcite precipitation occurred. And during that calcite precipitation, between 7 and 40% of the iodine within those groundwater samples was incorporated and removed from the aqueous phase due to the co-precipitation with calcite. So now before we tie all of that contaminant information back into the remediation strategies, we'll summarize a bit of what we've learned about these contaminants. We learned that chromium can delay or prevent the transformation of vaterite into calcite, and the chromate ion can be directly substituted for the carbonate ion. Uranium can incorporate into calcite or be adsorbed, but the uranium speciation is very complex, and therefore its interactions with calcium carbonates are also very complex and very dependent on several factors, including the uranium speciation, the calcium concentration, and the pH. Iodine can be incorporated into the calcite structure when it's in the oxidized iodide form, but does not incorporate when it's in the reduced iodide form. And that's important because depending what form the iodine is in a remediation site will determine whether or not, or to what extent it is affected by the calcium carbonate presence. It's also held mostly at the surface of the calcite particles, even when it is incorporated. And with that, we will pass it back to Nick, who will start tying this all together with a remediation perspective.
So in the previous slide, we showed how important are the interactions between different contaminants with the calcium carbonates. We talked about absorption of contaminants to calcium carbonate. We talked a little bit about the co-precipitation of contaminants with calcium carbonate that act as a solubility control partitioning interaction with respect to slowing contaminant transport. As an example, within the plume, especially at the distal portion of the plume. We talked a little bit about the co-precipitation with calcium carbonate that provide a continuing source of contaminants. Example for the tail of the plume or near former source areas. And we also talked a little bit about the low solubility compounds that are formed as a result of calcium carbonate dissolution. For all these reasons, the interactions of calcium carbonate with different contaminants are important in the development of conceptual models, are important and should be incorporated in the managed natural attenuation evaluations, and in some cases are part of an efficient remedial strategy. Next slide, please. This slide actually re-emphasizes the fact that sometimes the calcite saturated with contaminants actually can serve as a source for contamination. And this is another example taken from the 300 area sediments at the Hanford sites, where the changes in the river stage resulted in the release of uranium from carbonates. And of course, understanding of carbonates and their role in the uranium mobilization helped to determine the continuing source of uranium in this area. Next slide, please. Conceptual site models are an essential first step for creating remedial plans for a complex site. This is a quote taken from the Interstate Technology and Regulatory Council that states that a thorough conceptual site model can best represent site complexities and define remediation potential based on site complexities. And we really think that complex sites where calcium carbonate are present should include carbonates in the conceptual site model and all the reactions that are associated with the presence of calcium carbonates in those sites. Next slide, please. I want to bring here to your attention the monitor natural attenuation as an alternative to direct remediation interventions. M&A relies on natural processes that will reduce the mass, toxicity, mobility, and/or volume of the contaminants. They are part of a carefully designed, controlled, and monitored site-specific remediation strategy, and they provide an effective knowledge-based remedy alternative for sites that are difficult to access with high degree of heterogeneities and where the traditional remediation technologies are difficult to apply. And it is usually combined with long-term monitoring as well. Calcite-based processes provide an M&A pathway especially for the uranium, chromium, and others that are important risk drivers, especially at the Hanford site. Next slide, please. I want to bring to your attention one fact, though, that is kind of an important and is directly related to the way that carbonate minerals interact with contaminants. Groundwater and vadose zone pore waters may have, in some cases, elevated CO2 levels. And these CO2 levels can result in the high CO2 partial pressures that are in some cases 10 to 100 times above the atmospheric level. And we have actually noticed that when Hanford groundwater samples are brought to the surface, they undergo significant CO2 outgassing. This is an important thing because elevated CO2 partial pressure are a result of decomposition of organic matter or deposited organic matter that, although is scarce in the Hanford site, we do have some organic matter presence there, or are created as a result of as infiltration passes through sediments and it dissolves CO2 and it carries it down. So the partial pressure of the CO2 down in the subsurface is built up. All these circumstances provide a means to include calcite precipitation, to induce calcite precipitation in the subsurface. And inducing CO2 outgassing from solution will result in calcite precipitation. A study conducted in 2015 clearly showed that as a result of outgassing, calcite was formed in the groundwater samples taken from the deep subsurface that were contaminated with iodine. And a good portion of this iodine actually was taken out of the solution and it was incorporated into the precipitating calcite. But the main point here is that it is very important for us to understand the carbonate system under field conditions because it might be different from what we can actually evaluate from the surface. And this should be an area of focused research work. Next slide, please. The remediation through induced calcite precipitation can involve for one example would be the barometric pumping that could be used to reduce the CO2 partial pressure in vadose zone and groundwater to induce calcite precipitation and remove contaminants from solution via this reaction. If necessary, and if it is effective implementation, and if effective implementation approaches can be developed, calcite processes could be applied as an active in situ remediation to enhance attenuation as well. And these active approaches could involve formation of calcium carbonate in the subsurface via injecting calcium carbonate forming solutions, or perturbing the subsurface geochemical system by injecting, for example, CO2 gas in the subsurface to induce initially mineral dissolution. And then when the system gets back and equilibrates back to the initial conditions, the reprecipitation of a carbonate can be induced and can be promoted. And as a result, the contaminant can be removed from the aqueous. Next slide, please. In the very last slide, I wanted to show you some effort that we did to study the complex reality of the Hanford site. Many contaminated locations at the Hanford site have overlapping plumes of different contaminants, and remediation of these sites presents a unique set of challenges. We published a paper in 2018, and Amanda Lawter was the leading author on that. Well, we tried to understand how two different technologies, one that was used to remove technetium contamination and another one that was used to remove iodine contamination, interacted with one another. The ZVI and SMI were used as strong reductant to remove technetium from the aqueous phase via reduction. But applying ZVI and SMI in the subsurface also reduces iodine. The predominant species, as Amanda mentioned, of iodine in the subsurface is iodate. But when you apply a ZVI or SMI in the subsurface to remove technetium, what you also do is that you can reduce iodate to iodide. And then if you apply like a calcite remediation method to remove iodate, iodine cannot actually, as iodate cannot actually get into calcite because it has been already transformed to iodide, and iodide is not able to get into calcite. So finding ways to actually apply those methods sequentially would have been a better solution in this case. I just presented that as an example of the complexity of the reality at Hanford, not only in terms of the overlapping plumes with one another of different contaminants that actually exhibit different geochemical behavior, but as well as when we design, to emphasize the fact that when we design remedial strategies, we actually to think about the effects that those strategies might have, not only on the specific contaminant that we are interested at that particular time, but for other co-contaminants as well. And with this note, I would like to complete our presentation and take any potential questions.
Excellent. Thank you, Nick. Thank you, Amanda, so much. We have about 8 minutes left, and I am going to start with a question that we received in the chat box from Kelly Houston. This question is for Amanda. Amanda, regarding the calcite and chromate chemistry discussion, does chromate incorporation into calcite serve as a residual source or sink related to a chromium groundwater remediation strategy, or both?
That's a great question, and it can actually be both. So we actually do have some new testing we'll be doing soon where we're actually going to try to dissolve the carbonates in the subsurface and flush out the chromium so that it can then be treated by a pump and treat system. So in that case, it would be the source, and it has been identified as a potential long-term source of chromium at the Hanford site. But in other ways, inducing calcium precipitation could also remove that chromium. It's just a question of how immobile, or what time scale will it be immobilized for.
Gotcha. Great. Well, thank you. Another question: how do calcium carbonate minerals compare to other minerals in terms of reactivity, contaminant affinity, and removal? So Nick or Amanda, either one of you want to tackle that one?
Amanda, you want to take it?
I think that one's more for you, Nick.
Okay, I'll be glad to address that. Usually calcium carbonate, if you compare calcium carbonate, for example, with iron oxides or phyllosilicates that occur in the subsurface, they are not as good as them. But however, I mean, I want to stress the fact that calcium carbonate is ubiquitous. It's present in every kind of environment almost. And it's always present in substantial quantities. So from that point of view, it might be very important to look at the calcite as a sink for contaminant as well. But yes, comparing to other actually pretty reactive minerals like iron oxides, they are less reactive. As a matter of fact, there are studies that show that if an iron oxide is covered with a layer or a coating of calcium carbonate, then that iron oxides or the whole system becomes less reactive to different contaminants. But that's a good question.
Great, interesting. And I think you kind of answered this question a little bit in your answer, but we just had another question in the chat box. So why calcium carbonate and not another natural material for remediation of chromium or uranium?
So we were focusing on carbonates. As Nick explained in the introduction, they're ubiquitous, they're everywhere, and even a small amount, 1% in the sediment, will dominate the chemistry. Specifically at the Hanford site, we have high amounts of carbonate, and so in the site that we're most familiar with, it really does dominate the chemistry. In other minerals could also be potentially used, and that's kind of where some of the complex site, the conceptual site model would come into play, where you really have to look at your site and look at all these little pieces to determine what's best for each site.
Gotcha. And a follow-on question to that from the same person: do you think about a mixture of calcium carbonate with another one would be more effective?
Yeah, I will take that, Amanda. I can take that question. Yeah, absolutely. Mixtures of calcium carbonate with other sorbents that might be much more effective, it's not at all a bad idea. However, one should actually look carefully at the sites, at the specific site and specific conditions when decisions like that are being made. That is very important.
Okay. One more question that came in through the chat. Are there any carbonate minerals that could precipitate in the subsurface that could act synergistically or not with calcite for sequestration or entrapment of contaminants?
We've actually looked at, we use some different synthetic groundwaters and synthetic pore waters in some of the studies that we've done regarding iodite and chromium in calcium carbonates, and found that those additional components do make a big difference. We haven't looked into it far enough to see specifically what was making the difference, but certainly that can have an effect.
Okay. Nick, do you have anything you want to add there?
No, I think Amanda covered it pretty well. That answer. Yes, it's a good question though, because yes, you might be able to form some other carbonates. For example, in the case of uranium, you might have a pathway of forming aragonite or other carbonates for that matter, and then you might have a chance of removing much more uranium than what you could remove via calcite precipitation. So that's a great question.
Great, excellent. Well, thank you both, and thank you everyone for joining our seminar today. Just a reminder that today's seminar will be archived on the RemPlex website. We encourage you to sign up for the RemPlex newsletter by sending us an email to remplex@pnnl.gov. A couple of you have already done that since the beginning of the seminar, so thanks. And also we encourage you to join our LinkedIn group. I put that link in the chat box, and also take the survey. So again, thank you. Hope you had a happy Thanksgiving, and we'll see you soon. Thank you, Nick. Thank you, Amanda.
Thank you very
Thanks,
much.
Alicia.
Bye, everybody.
Bye-bye.